Okay. Wow, this is hot. um, hey, folks. My name is Denzel. I am a principal product manager in the Azure Database for Postgres team. I've been in Microsoft for a while and worked on all sorts of data technologies, primarily relational, but also kind of some of the analytics space. So I've been in Microsoft for a while, did product management in SQL, now I'm in Postgres, and did multiple field-facing roles. So today I'm here to talk about PostgreSQL and what is attractive in it for devs or to build new applications. And it's just 30 minutes, so I'm going to pick and choose a few things because there's no way I can cover the spectrum of things. Right? So first of all, it's community-driven, it's OSS, it's portable. You have great community support and resources. Extensibility is a great reason, and we'll see some demos around that. You have a super rich programmability surface area. And then there's standard compliance and price performance. Now, Postgres by itself has a lot of things going for it, which will cover some of these. But outside of Postgres also, Azure builds upon it, right? And the way we do that is offering it as a managed service. So you have built-in compliance, you have security, you have all sorts of private link and AAD authentication. You have high availability with replicas and read scale-outs. I'm not going to touch on the details of all the PaaS services. We'll look more at the Postgres feature set for devs than actually the rich services that are included. Also, I wanted to put a plug for kind of the session that Charles is giving at 1:30, which will cover all the new announcements. And there'll be a lot of demos on kind of the SSD v2 for performance or the GODR, downtime scaling, so on and so forth. So those are things I'll reserve also for Charles's session, and we'll cover other stuff here. So needless to say, Azure builds upon this, gives you kind of the managed platform feel, which is intelligent. You have help in parameter tuning, rich diagnostics with query insights, security, and so on and so forth. Again, plug for the 1:30 session, which is a 75-minute session, which will cover all our Ignite specific announcements this week, which are in preview, right? And now, the other reason you can bet on kind of Azure is our roadmap. If we look at kind of our delivery rate over the last year, we have delivered and shipped a bunch of features, and we're doing this as a rapid cadence, right? From AAD support in Q1 to read replica support to Postgres 15 and query performance insights to storage auto grow. And I'm just picking a few things. And automation tasks and cross-subscription resource. And then look at Q4, the slew of things that we announced at Ignite, right? So, we are invested in making this the best Postgres experience in all the clouds, and this release schedule should assure you of that. Now switching to kind of why build on Postgres, right? And we'll look at a few things. Developers some of the indexing things on Postgres. You have various types of indexes. B-tree for equality, you have and range, you have hash for equality, you have GIN type indexes, which are inverted indexes, which are great for searching arrays and other data types in Postgres, and we'll see examples of that. The gist and SP-gist indexes, again, for spatial type of data. And then you're able to do partial indexes with a filter or indexes on expressions which are complex as well. And we'll see that in a demo. And with the extensibility extensions also, which define new data types, can overload these index types to actually give you indexing capability. So let's look at a demo. In this demo, a couple things we'll see. One is some of the indexing things we talked about. The second thing is the Azure Storage extension. This is a first-party extension that we've released and previewed, which allows you to interact with Azure Blob Storage and load data from there, copy data from there, list blobs, so on and so forth. So it makes it easy to kind of load data which exists in blob. And we look at the PGTR GM extension, which is trigam matching. and that's more as a part of Postgres that effectively breaks strings into trigrams to support things like similarity searches. So let's go and look at this demo. So I have a recipes table here, just a simple recipes table. And then if I look at that, the storage extension is loaded. I've already preloaded and configured the key to my storage account because I'm going to load from there. So the first thing I do is I can kind of list the blobs or the files on storage account. You just specify the storage account and the container, and you see the blobs. I'm going to take this 2 gig recipes data.csv and load it into my recipes table. And I can do that with the copy command. So the copy command, now you just point to the blob, load that data. And you can specify other options here. The format is CSV. We don't still have Parquet support. That's a request. But you can also do insert, select, and transform this data on the fly. If you want to cast a column or just have a subset of columns being loaded, you could do an insert, select instead of a copy command. And we have loaded 2.2 million rows here into this recipes table, right? So now if I look at kind of the table itself is about 2.1 gigs in size, which contains this 2.1 million recipes, if you will. Now I'm issuing a statement, and the statement has a leading wildcard, which is %strawberry, right? So it's going to search all those titles with the leading wildcard. And most of these, this takes 727 milliseconds, and most of the engines in leading wildcard cases do a scan, right? So this is doing a scan right now. I don't have an index. And it's filtering out a ton of rows, which is 735,000 rows are being filtered because of that leading wildcard for strawberry. The other thing I can do is I can do regex pattern matching. So here I have title, which is strawberry or raspberry. Regex has great support here. And again, I don't have yet an index. So the time is a little more because we're doing a more comprehensive kind of pattern match. It takes 1.1 seconds, if you will, and it's still a scan. So now what I'm going to do is I'm going to show you, these are extensions. To create an extension, I have to actually allow list an extension in Azure. TRGM is actually allow listed, and I'm creating the extension. So creating extension Postgres is as simple as that. And now what I do is I create a gin index on the title, which is an inverted index. And this is going to help kind of some of the searches, right? So gin index, as we talked about, is an inverted index. It's great at searching kind of arrays and some of the complex types, right? So with this index created, let's see if kind of some of the searches that we have done matter. And this index is actually pretty small in size. It's a 2 gig table. The index size is only 136 MB. So from a space perspective, it's not taking a ton of space, right? So same queries will run again. Strawberry. The leading wildcard still has reduced now from 700 milliseconds to 44 milliseconds. And now we pick that index for this query, which is awesome. I mean, many relational databases don't kind of do that. Similarly, for the pattern matching where strawberry or raspberry exists in the title, we pick this index. The time drops from 1.1 seconds to 101 milliseconds. A huge kind of improvement in time, even for the pattern match, which was a regex expression index is picked up. So that's an example of kind of some level of indexes. The other reason is data types. There is a rich ecosystem of data types. You have text, numerics, date, and time, which exists in many places. You have enumerated types within you have arrays. JSON-B support is really awesome. The geometric types are great. Range types, composite types. I could go on, and this demo would not finish. And then the programmability. You have table inheritance. You have declarative partitioning, and multiple ways to actually pattern match in this case. So let's look at yet another demo. So this demo will be more on JSONB. We'll see a subset of the JSON operators. It has a rich set of JSON operators and functions, and some of the indexing to support pattern matching. So if we take that same kind of data set, right, you can do a row to JSON function call, and we actually will convert that row to JSON. Not hugely useful. Instead, I can take and I'll show you the function. I can actually typecast and form my own JSON from a set of columns by using JSON build object, where I choose the columns I want. I can typecast as I want. And I'm going to convert this actual table, the recipes table that we saw in the previous example, to JSONB. So I create this table, recipes JSON, and see what that experience would be if that same table was in JSON. So I'm inserting into the JSON table, building JSON object. And here I'm doing a regex replace to remove some special characters out of kind of the text in line as I'm creating the JSON. And I'm doing that both for directions and the ingredients column, typecasting to JSON, and actually importing it into this table. So this should finish, these 2 million rows should finish in a second, but it'll result in a JSONB data type, which is a binary JSON data type. And you see the 2 million rows. Now I can start accessing elements, and accessing elements is as simple as saying, a data title, which will give you the title, and I'm doing a limit one, which is the top, one row. Similarly, if I look at ingredients, the ingredients is more of an array, right, nested, which has, the first, second, third ingredient in the recipe. I can access elements out of the ingredients just by putting a, index 1 will give you the first element, and so on and so forth. So, support is pretty rich, from that perspective. And then I can search queries. So I can say where ingredients equal to cake or contains cake. And in this case, actually, I get still a parallel scan. I don't have any indexing enabled, right? So I have a filter. It's 699 milliseconds. For that query, but searching still works. Now, what if I use a gin index, and this is the data path ops type of index? So this only contains specific path operators, if you will. So I create the index, and I'm going to run this query again and see if this helps, right? And like I said, the data path ops actually only helps for path type of operators, so it doesn't help. The execution time actually doesn't really go down. It's still a sequential scan. Now, if I switch the operators to a path operator which says, hey, the right side belongs, is contained, or data contains those ingredients of cake, then you see that you use the index. The time drops from 1.2 seconds to 1 millisecond. Uses the index. So that's another path operator that exists in this, and we pick the index, and time is specifically better. Now you'll see that since we index the entire JSON, the JSON index itself is almost the size of the data. You had a 2.2 gig table, a 900 MB kind of index, which is pretty heavy, right? So similarly, I can create a gin index on an expression. And here the expression is just the data ingredients, which is the ingredients array. And this reduces kind of the size of the index that is needed and will enable me to pick that up for the other queries which are not path queries. So if I look at size of the index, that size of the index now reduces to half of what it was before, right? And then if I run the query, the original query, which is ingredients like cake, it's picked up that index. The time drops from, I don't know, what it was 700 milliseconds to like less than 1 millisecond, right? So it picks up the gin index, which was a gin index based on an expression for this query. Last but not the least, if I look at the size of the table, the size of the JSONB table is not fundamentally different than the size of kind of the base table, which was not JSON, right? So it's pretty, close in size from that perspective. So That was the second demo, if you will. I should actually look at the time. OK. Another reason is, I mean, extensions, as we talked about, are super great in Postgres. It's built for extensibility. There are a ton of extensions. We ship around, I think, 70 extensions on Azure. And most of the common ones for sure. But you have buckets of extensions. For example, admin has cron and auditing and so on and so forth. On the AI and ML, which we'll see a short demo of, we have Azure AI, which was seen in the keynote. How many of you were in the keynote this week? Have you seen? OK. So some of you have seen that. And then we have vector data type with the PG vector. Geospatial has PostGIS and a bunch of the others. So it's strong from a extensions support. And you need to allow list extensions, as shown on the right. So you go to Azure extensions and allow list whatever you want. And then after that, creating extensions is just like normal Postgres. So let's talk about the Azure AI extension in a second. And I'll show a short demo, which is different kind of than what you saw in the keynote, with some different aspects to it. So the Azure AI extension allows you to actually call into Azure OpenAI and create embeddings with a single line of SQL statement. It also allows you to call into cognitive services, Azure AI language services, and invoke things like sentiment analysis, et cetera. And it's complementary to vector data type, which actually stores that vector data and within the database and can be indexed, and you can use similarity searches efficiently. So you don't have to use an external vector data store, and it's cost efficient and performant from that perspective. Right? So that's kind of the intelligent AI. So let's look at a demo for this. OK, so I'm going to drop this table, summaries. I already created and configured. Wow, it's taking longer than I thought it to drop. OK. I hope it is not. Let me see. I hope it's not my firewall rules or something like that. OK, it's back. So drop table. Neighbor is reestablishing. OK, it doesn't exist anymore. Drop table this. So I've already configured the Azure AI extension, and my endpoint is there. I don't want to actually publish my API key here. So I go ahead and create this build summaries table. And then what I'm going to do is I'm going to load some data. Shoot, I should have prepped for this a little bit better. So I'm using the copy command and loading some data. This is just a client-side copy. I just pulled some data off GitHub and loaded some rows into the table. The next thing I'm going to do is I'm going to add a vector column. So let's do a select, actually. Select star build summaries. So a select of this will show you it doesn't have too many rows. It has 20, 30 rows. Oops. Build summaries. Did I not? Where did I copy? Oh. OK. Let's try this again. Build summaries. OK, it did copy this time. I don't know what happened. It probably lost the connection before. And this is actually large text, so they're documents, which have some builds. And the build text is pretty big. So what I'm going to do actually here is add a embedding column. So I'm adding a vector column. And in vector column, you have number of dimensions, and that depends on kind of the embedding you're generating. So in this case, I'm calling it to OpenAI, so I'm going to generate like a vector of 1536 dimensions. So I'm adding this, and there are multiple ways to kind of do this. One is you can just update, as you need and generate the embedding. And this doesn't have to be, the column doesn't have to be in the same table, right? It could be modeled with a key and another column. This is just for simplicity that I'm adding it to the same table. And then, you populate. So if you look at the vector now with that update, this vector is populated, which is a huge number with embeddings. And then I skip to the next step where, you could alternately, instead of adding just a column, you could make it a default. So in this default, I say I add this vector column, and I generate as always, and I call this OpenAI create. So I'm doing 3 things here, right? So I'm calling this, I'm adding the column, and I'm generating it. So if you do that, of course, as you insert, embeddings will be generated. Then the next step is creating indexing on any of these vectors. And these indexes that are created are depending on the query types. If you're doing a nearest neighbor or an L2 distance search or a cosine similarity, so there are different types of indexes that can be created. I'm going to try a cosine similarity. So I create an HNSW index for cosine similarity. And I'm going to do a simple search here and show you what. So this search is not very impressive because if I do this search, and I'll zoom in a second, I say show bills relating to veterans who are entrepreneurs, right? OK, the first result I get is, of course, even a text search would probably get me this. It's not like very impressive at all. So what if I do kind of something like this? Can my mother, Marine, get financing to open a business? Nothing to do with the bill itself. Would that actually work? And so what I'm doing here is I'm getting the embedding of my search string from Azure OpenAI by calling this create embeddings procedure. And then I'm doing a cosine similarity search with the vector column that I had stored, right? So I'd done an update there for every row in that vector to get the embedding. And so it's going to match it and give me the rows that are similar. So if I do a limit 5 here, it'll give me the top 5 similar embeddings. And yes, it gave me that the same kind of act. And just to show you kind of what the embedding was generated on this bill text. And this bill text is like huge. There's no word mother or marine anywhere in it. It still was able to get the semantic bill that would help in this case, right? So that's one example kind of embeddings. If I use traditional approaches like or full text, even if I looked for those clauses, you would get no rows. This is using case insensitive or it would get some rows, but it has nothing to do. This is a build to improve data collection. This is to amend marine mammal protection. It has no semantic similarity to the question I actually asked, right? So that's second thing. Similarly, with full text search, you wouldn't get that, that data either. You wouldn't even, and if you search the whole string, there's no way you would get it because the bill doesn't hold the whole string, right? So that's that. So we could use, besides this, there's also Azure Cognitive Services. So if I do here df plus Azure Cognitive .star, I get a bunch of cognitive services. One is sentiment analysis. Let me zoom in here and see if I can make this a little bigger. Oops. OK. So yeah, one is sentiment analysis. The other is language detection. Then I have extract key phrases. There are about 10 or 15 different functions that we support. You can look up the docs for that. So I'll try this summarization, which is an abstractive summarization. I'll limit it to 1 row. And it's the same bill that we were talking about here. And so this enables me to actually summarize this whole bill in 1 row. And so this whole bill is summarized to, let me scroll up here somewhere, to this paragraph. So this gives me a summary of the whole bill, which can be generated as an abstractive summary. Similarly, I can do things like give me an extractive summary. And an extractive summary, OK, so let me talk about two more things. Both the summarization return complex types. They return an array of sentences which form the summary. And so this unnest here was actually breaking that out into multiple columns, right? That's all that it was. So similarly, kind of if I do the extractive summarization actually has to quote exact sentences from the bill, which are key sentences in the bill. Unlike abstractive, which kind of summarizes into a paragraph, this actually has to quote the bill. And so this is another example where the Azure AI language services help quite a bit. And you'll see citations kind of pretty much from this bill. So this act may be cited, whatever. Some of the main key phrases here. The last but not the least, the last thing I'm going to do is I'm going to do some key phrase extraction example. Here I have an example of a phrase, and I like the Mavs. So their star player is probably an MVP candidate this year. So if I pass this text to kind of what are the linked entities that it can extract, from that phrase it extracted the name of the star player, the team, NBA, and MVP. And it even gave me links kind of for supporting information and wiki URLs and things of that nature, and classified kind of the confidence scores for each of those terms. So there's a bunch of stuff you can do. Just check the Azure AI extension out. And we would love to kind of hear feedback on what that is. The next one is spatial. Spatial, Postgres is super strong in the spatial needs too. So PostGIS, is a very common extension. Gives you a lot of spatial or geometry and geography types and spatial abilities within Postgres. And you have a ton of related kind of extensions. If you have PostGIS, but you have the decoders, and you have routing and raster, and this. So, and it supports a bunch of indexes, a bunch of functions to do area and intersection and overlapping distances and maps. So let's look at the demo if I have time. OK, 12 time. I do have time. Flip to demo again. So here I have kind of the NYC database. So it has kind of neighborhoods and train routes in New York. This is the data set that downloaded from Kaggle. And I hope I've not lost my connection again. I think it's trying to re-establish connection. Sorry. OK. There it is. So these are my tables. Oops. Seriously. These are my tables, right? And these all have a geometry type. Each of these have a spatial reference code, if you will, which tells you what the units of spatial are. For example, is it in meters or in degrees, so on and so forth. So there's an spatial reference code that gives you kind of the types. And if you had to explore this out, it would give you kind of each type and what are the metrics. So you could do things like, so let's see if the geometry viewer, it's not been very kind to me today. So pgadmin has a geometry viewer. It's not been kind. I think my data has a geometry type which isn't good. But you can do things like select the area of a particular geometry for a particular neighborhood, right? And so this would give you kind of the area of a neighborhood, if you will. Then you can do things like length of the streets. And I'm not even going into more of the advanced things like routing. So length of the streets by kind of street. By type, sorry, you'll see. So you see residential is at the top, followed by motorways, so on and so forth. More complex, that's easy. So what about intersection? So let's say you wanted a subway station for Broad Street. Right, so the subway station for Broad Street is a point, right, on the map. It's a point on the map. I take that same point and I pass it to, and I could do this with a join, but I just wanted to simplify the query. And and I could get the intersecting neighborhoods, if you will. So the intersecting neighborhood for Broad Street is financial districts, and it's in Manhattan, right? So that's ST intersects, which can take a geometry and intersect it to the point or another geometry to see if there was. So other things like get me within 20 meters of kind of this street of this point, get me all the stations. If I can, my mouse is not cooperating right now. So within 20 meters of this point, there are these three stations, if you will. Similarly, you can do things like population distance. I know I'm at time. So there are a bunch of other things we can do. I can share these demo scripts, kind of upload it on the slide. So it's a very rich experience on PostGIS on Postgres. Let's switch to the slides. Last but not the least, check out our Ignite link. There's a bunch of new things we've announced and documentation. So all is recapped within here. And again, a plug for the 1:30 session, which has like a ton of demos on new things that we, as a service, we have introduced outside of Postgres as a code native experience for devs, right? So feedback, please, and appreciate your time. And sorry I rushed through.